formally, let me start our seminar. And today we have a talk by Professor Alvaro Liendo from Talca University, Chile. So, Alvaro, you're welcome.
So thank you very much. So thank you very much, all of you, for being here. As I said before, it's really nice seeing you guys after such a long pandemic time, and now also travel quite restricted between probably Chile and Russia. So this is the network with Adrian Regueta and Christian Ure. And I checked on your seminar, you had Andrew Regueta maybe 1 year or almost a year ago with a similar talk. It's not exactly similar because we're talking mostly about surfaces here. So, and he talked about toric varieties.
I'm
so
sorry.
This is a principle. Yes.
I'm sorry, but I don't know about other participants, but for me, a sound is not some waves in the sound. If you can change something, I don't know.
Maybe some reverberation.
Reverberation, it's strange.
Sasha, do you see?
But maybe.
No, it's not very clearly.
When it's reverberation, it's very usual someone else's microphone that is on, not mine.
Oh, I guess now it's okay.
Now it's became better. Mm-hmm. Okay.
No, it's okay. Okay, let me check the participant list. So
You're going to remove somebody from participant list, and then sound will be better.
Yeah, I'm checking whether someone has microphone on, but it's only you. It's okay.
Okay.
Okay. If it goes bad again, you just stop me and we do something. Okay. So as I said before, you had a similar talk. Wait, I forgot. You had a similar talk a few months ago, maybe I think it was last March, by Andrew Regueta on a similar subject of this paper. Good. But I'm concentrating more on things that that shouldn't intersect with what he told you. So the title is Characterization of Algebraic Varieties by their Group of Symmetries. It's a very simple question. So the question we want to answer is a geometric object uniquely determined by its symmetry group? So that's the question. So let me start with some very simple example. So let's have a triangle here. So the first one is a triangle. So what's the symmetry group of such triangle? So the symmetry group of something like that is the dihedral. You can call it D3 or D6. Actually, preparing this talk, I learned that it's not so clear. I don't know what the Russian notation is, but it's not so standard whether 6 or 3. So it's the dihedral, that happens to be the symmetry of the triangle. That's why you could put 3, but it has 6 elements, so you could put 6. Finally, doing some Google research, I concluded that D6 was more common name for this group, so I call it D6. And similarly for the triangle, the symmetry group of the triangle is D8, the dihedral with 8 elements, sometimes also called D4. Again, as I said, it depends on who wrote the book, the name they gave it. So, in general, if you have a polygon with n sides, the symmetry group of this polygon is going to be the dihedral 2n that happens to have 2n elements. Again, you could call it dn. In my mind, it's called dn, but Google told me it was more common to call it like this. So, in particular, what you can conclude from this is that actually regular polygons are uniquely determined by their symmetry group. Since, for instance, if I draw a polygon here, a regular polygon, you have to believe it's regular. It doesn't look so regular. And then I cover it. I completely cover it so that you cannot see it. But then you can ask me any question about the polygon. You just have to ask, okay, any question about the symmetry group? So how many elements does the symmetry group have? And I will have to tell it 12. And you will say, then it's an hexagon. And then you will see, and it really is an hexagon. So you can actually know the polygon I had by just knowing the symmetry group. So that's the question we want to study in more general context. So let me go to the next simple example. So if you are doing polygons and you answer the question, the next thing you will try is polytopes. So let's try three-dimensional polytopes. In this case, there are not so many of them. There are only 5. They're very well known. They know like Platonic solids or other names. And then there is this 5. I'm always bad on the names. So you have the pyramid or the tetrahedron, the cube. Here, the octagon here. The octagon down here. Then you have up here, here's where I always make mistakes. So this is icosahedron, and this is dodecahedron, and then the last one is icosahedron. So you have these 5. And here, this is a picture is stolen from Wiki. All pictures are stolen from Wikipedia, but this in particular is also stolen from Wikipedia, and they stole it from a book by Kepler. So in this book by Kepler, the physicist Kepler, so you can see that Platonic solids are drawn one inside the other for some reason. And actually, this reason is not completely random. You probably know that whenever you have a polytope or any polygon or any polytope in any dimension in general, which is regular, you can create yourself another regular polytope. And you do this by just choosing the middle point of each face. So here's one middle point of a face, another 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 one, and another one. I don't care which middle point you choose. There are many ways to define the middle point, but for something regular, whatever middle you choose is the same middle. So just go the middle, and then takes convex hull. So in this nice picture, it's very clear that the convex hull of these 8 points is the octahedron. And this is not random. This one is called the dual polytope. And it's called dual not by chance. There is a good reason for it to be called the dual, because if you do the same process, so let me try and do the same process again. I'm taking the octagon that it's inside, and I'm choosing the middle point of each face. Something like that. Here, and then I take convex hull. Of course, when I take convex hull, all the lines that join segments have to be there. So we have that, we have this, we have this. And if you believe a little bit my drawing, which is not so good, you can see a cube again. So the dual of the cube is the octahedron, and the dual of the octahedron is back again the cube. That's why it's called dual. And now, imagine we have a symmetry of the cube. The symmetry of the cube will move the cube around, and this will move the middle points of each face somewhere, and so it will move the octagon, that is the convex hull of this set of points. So a symmetry of the cube gives us a symmetry of the octahedron, and the same way, taking a symmetry of the octahedron inside will move the cube, that it's inside the octahedron. So you have it's very easy to see that this map is injective, because if you're fixing all the middle points of all the faces, you're fixing everything. So it has to be injective. So this gives you an injective map from the symmetries of the cube into the symmetries of the octagon, and also an injective map from the symmetry of the octagon to the symmetries of the cube. So they are the same, which is what's written here. So for polygons, the answer was affirmative. I can characterize the polygons with their symmetry group, but for polytopes, it was no longer the case. Because, for instance, the cube and the octagon have the same symmetry group. The same would happen here with icosahedron and dodecahedron. And then the dual of the tetrahedron is again the tetrahedron, so nothing changes. So, but in this case, we have negative answers. So regular polytopes are not uniquely determined by their symmetry groups. And if you're wondering why didn't this happen when I did polygons, it's simply because the dual of a polygon is the same polygon. So dual have no real interest when I do polygons. So if this is my polygon, I take middle points. I can do it again. I take convex hull, and you see I get again. I took a square and I got a new square. So will not help me in any way in the case of polygons, but for polytopes of dimension 3 and higher, it works. Actually, the answer will be negative in any higher dimension. Good, but let's go deep into geometry, or deeper into geometry. What happens with differential geometry? So a differential manifold, it's the picture that's there. So it's something that it's locally like the Euclidean space, but not globally. For this particular case, there is a very strong result. So you can actually give a very strong result, which it's already pointing in the direction of the kind of results I want to show you. So if you have any isomorphism between the diffeomorphism group of two differentiable manifolds, then it has to be induced by a diffeomorphism between the manifolds. So let me explain what this means. So maybe actually the result, let me first give the result. Yeah, I thought I had. Well, let me write it here. So let me explain what this means. If you have a manifold, sorry, I put here. If you have a manifold M and a manifold N, and you have some diffeomorphism between M and N, now you can take the group of symmetries of M, which is in this context is called diff, so the group of diffeomorphism. And you can create yourself an isomorphism. So if phi is a diffeomorphism between M and N, you can create yourself an isomorphism between the diffeomorphism groups, which is just take any diffeomorphism here that I'm going to call F, you just take it to whatever it has to be. So you want to have something that starts in N. So you take phi inverse, so you go from N to M, then you take F, and then you take phi. There. This conjugation gives you an isomorphism here. Okay, the theorem by this Philippietics says that actually any isomorphism, if I have any isomorphism, then there exists this phi, such that the isomorphism that a priori was just an abstract isomorphism between these two groups that are grouped without taking into account anything, the fact that they come from something geometric. If I have any isomorphism between this M and this N, okay, this any isomorphism was not just any, it was coming from conjugation by a diffeomorphism of from M to N. So it's really strong result, saying that actually, even if you try to forget geometry, geometry is still there. So whenever you have isomorphism between the groups of diffeomorphisms, it has to come from a diffeomorphism itself. Okay. So this allows us to conclude in the strongest possible way that differentiable manifolds are indeed uniquely determined by their symmetry groups. Okay, so we can now come back to the original question. So is a geometric object uniquely determined by its symmetry group? And you all know I'm an algebraic geometer, so actually I'm interested in the question from an algebraic geometry point of view. So let's go to algebraic geometry. Just a slide to remind you that we actually do algebraic geometry. So there are two things to take into account. So if you have an affine variety, sometimes you are interested in taking it projective or complete. So that's very common for everyone except us, no? So almost every algebraic geometer does compact stuff. We are affine people, so we like affine stuff. So we're going to be working mostly on the affine case, but I'm going to give you some negative results for compact case. Okay, let me also remind the kind of morphisms we have, because in algebraic geometry we have two notions of morphism that are both equally good, one or another. So we have regular morphisms, which are morphisms given by polynomial or locally polynomially, but since I'm going to be taking only affine varieties, they're going to be polynomial. So here's an example of a regular morphism from C2 to C2 or A2 to A2. But we also have rational morphisms. Rational morphisms are morphisms that are given by quotients of polynomial, and as such, they are defined only on an open subset, because you have to remove the set of points where the denominators vanish. And if you have these two kinds of morphisms, you have two kinds of symmetries or of automorphisms. So our two possibilities for symmetry are regular automorphisms that we denote by alt x, which corresponds to simply polynomial maps and admitting an inverse, which happens to be also polynomial. So there is one classical example of an automorphism of C2, which is just taking x comma y into x comma y plus any polynomial depending on x. It's the most basic example of automorphism, of triangular automorphism. Its inverse is just taking minus sign there. If you compose those two, you get back to the identity. And we can also have birational automorphisms, but here is a birational automorphism of C2 or of P2. Since they are only defined in an open set, they are the same for two varieties if one happens to be an open set into the other one. And the example I gave is just xy goes to 1 over y, 1 over x. And you also see clearly that it's quotient of polynomial, it's inverse, it's also quotient of polynomial because it's herself. So the same map is its own inverse. If you compose two times, we are switching x and y from denominator to from the top of the fraction to the lower part, and also from first coordinate to second coordinate. If we do that twice, we get back to xy. Of course, the automorphism group is always going to be contained into the group of birational automorphisms, since okay, one is clearly a subset of the other. Automorphisms are just birational automorphisms defined everywhere. So if you are defined everywhere, then you have no denominator. Good. So this is just basic notation. Let me now talk about these groups a little bit. Okay. Again, probably you all know, but these groups, sometimes they are some monstrosities. So BIR, so the group of birational automorphism of Pn or of Cn is, in algebraic terms, correspond to this group. So the group of automorphism of a purely transcendental extension over the base field with n variables. And it's a monstrous group, which we really understand almost nothing. We understand a little bit when n is 2. Again, we understand very well when n is 1. Almost something, or not that much when n is 2. And from 3 above, it's completely hopeless. And now if you take regular automorphism of P, I didn't wrote it, but Pn is boring. It's a very simple automorphism. It's PGL n plus 2 over the base field. So I don't put it in this list because it's not a monstrosity. It's a linear algebraic group. It's a nice group. But the automorphism group of non-compact varieties can become quite monstrous. So if you have the affine space, this time is algebra automorphism of a polynomial ring in n variables over the base field, which is again a monstrosity. A little bit less monstrosity than Cremona, because for n equal 2, we actually know what it is. We understand it quite well. But starting from n equal 3 above, we understand very little of the structure of this group. Good. So let's come to some compact examples before going to our main, to our results. So there's a very old, I forgot, I'm always putting the dates in these theorems, but I always forget, but it's 60 something, I think, old. Hurwitz's theorem says that actually, if you have a smooth, compact algebraic curve of genus 2 or more, then the automorphism group is bounded by a number. So the number happens to be 80, that depends on the genus. So it's 84 times G minus 1. See, the regular automorphism group is the same as the birational automorphism group for something of dimension 1 that it's smooth. Even normal is enough in general. So given this theorem, we can immediately say that actually algebraic curves, it's impossible that they are determined by their symmetry group. Since curves of genus 2, there are infinitely many of them. And in this case, the bound gives 84. Groups of order at most 84, there are lots of them, but it's a finite number. So there are finite numbers of group that could be the automorphism group of a curve of genus at most 2. And they are infinite. So it's impossible for the groups to classify the curves. So it's impossible for a finite set to classify an infinite set. So for algebraic curves, it's impossible to classify or to determine the geometric object by the symmetry group. This theorem has an analog much more recent than the previous one by Hakon, McKernan, and Shu, but it's in the exactly in the same spirit. So we fit a positive integer, and then there exists a constant that depends only on the integer, that I will call C, such that for any projective n-dimensional variety of general type, so general type for curves means genus 2 or more, then the order of the birational automorphism group, so the biggest one, you remember we had out and bir was the biggest one, okay, is bounded by a number, which this number is C times the volume of the canonical. It's not really important what this volume of the canonical means. For curves, it's G minus 1. So this is exactly the same as before. The previous theorem is exactly this theorem in which we know the constant for curves is 84 and the volume corresponds to G minus 1. But we have the same thing. So varieties, projective n-dimensional varieties of general type with fixed value for its volume of the canonical, we have infinitely many of them, and groups of order at most any number, in this case, C times volume of the canonical, it's a finite number. So algebraic varieties in general, it's impossible for them to be classified. So actually, this is even stronger. You can also, I chose this theorem because it's similar to the Hurwitz one, but you can also prove that if you are general type, so a generic variety of general type has trivial automorphism group. So most of them have no automorphism at all. So of course, the automorphism group is impossible to classify them. Okay, but let's now go into results that we will actually use and that are closer to what we do. So now you already see a famous guy there, so Cantat, famous among us. So Serge Cantat proved this one is 2006, this one I remember. Something that I was shocked when I saw it, that it needed proving. So it needed a proof, and an actual serious proof. It's not trivial at all. So it uses all his dynamical tools to prove that the groups bir Pn and bir Pm, actually they are different if M is different from N. So, or stated as is here, so bir Pn is isomorphic to bir Pm if and only if N equal M. Of course, this isomorphism here is just group isomorphism. There is no structure, there's no algebraic structure on Cremona group. So that's the main problem arising in all these notions. So the algebraic structure of the object does not reflect on the group, or we don't know how to have it appear in the structure of the group. So up to my knowledge, Cremona group is just an abstract group. It doesn't have any algebraic structure that we can impose on it. So in the same paper, as a corollary or theorem, maybe theorem because I put it theorem here, he proved the following. So we take an n-dimensional variety, just any n-dimensional variety, and we assume that the group of birational transformation of this n-dimensional variety is isomorphic as groups without any algebraic structure to the Cremona group. Then you can conclude that X was rational. Being rational means that you are equivalent to Pn in the category of rational morphisms, in the birational category. So this is exactly an affirmative question, answer to my original question. So rational varieties, meaning varieties that have an open set isomorphic to an open set of Pn, are indeed uniquely determined up to birational equivalence, which is up to birational morphism, among n-dimensional varieties by their birational automorphism group. So this is essentially affirmative answer. You see that the answer now takes 3 lines because I have to put some more precisions. In particular, I have this n-dimensional here. This doesn't exclude the possibility of having an n plus 20 dimensional varieties having the same isomorphism group as Cremona of dimension n. Only among varieties of dimension n, we can actually know if you have the same birational automorphism group as Pn, you were Pn up to birational equivalence. Good. So let me now in one line remind you what a toric variety is in case someone doesn't know, but I guess you all know. So let me just open the whole slide. So yes. A toric variety is a normal algebraic variety endowed with a faithful action of an algebraic torus having an open dense orbit. So, as an example, you have the affine space provided with a toric structure here, just multiplication in the open set isomorphic to the torus, and then it extends to C2. And toric varieties, they may be non-normal as well. So it's customary to call a toric variety a normal algebraic variety such that, yeah, so all toric varieties are normal, but I will need non-normal versions of them as well. So I call non-normal toric varieties. And here you have the most simple example of a non-normal toric variety. It's also the first example of a non-normal variety. So that's a thing, that curve has a non-normal singularity, and it admits a toric structure. Here is the toric structure for that cusp. Great. So actually at the original paper where toric varieties were defined, Demasure gave a description of the automorphism group of X. Even for complete toric varieties, not just for projective, as we were writing before. He actually just stated for smooth complete toric varieties because he was only interested in smooth complete toric varieties, but it doesn't matter. His proof works in general for all toric varieties. They don't need to be complete. And from his description, we can prove quite easily that for most complete toric varieties, actually the automorphism group is just the torus. It cannot be trivial, of course, because a toric variety has a faithful action of the torus, so it has at least a copy of the torus in its automorphism group. But for most of them, when you happen to be complete, that's all. There is nothing more. So it's clear that toric varieties are not uniquely determined by their automorphism group. So it's very easy. I guess mostly everyone knows. So we have been doing this demo. We have been stealing this Demasure stuff from Demasure for a long time already. So I guess most of you already know it. But I don't know if you draw something with enough rays, something like that, it already has no automorphisms. So that one has trivial automorphism group. And if you add one more ray, you remain being trivial. So not trivial, just the torus. I think so. Those two probably only have the torus of automorphism groups. I may be wrong. There may be some finite part in this example since it's extremely symmetric. But if you break the symmetry somehow, it will have trivial automorphism group, meaning for toric variety, just the torus. Good. So let's come to some theorem with affirmative answer, and actually which was proven by us. I told you this was with Andrew Regeta and Christian Urech. I didn't say, but I guess you know them all. So Andrew Regeta, he is Ukrainian, now in Germany, in Jena. And Christian Urech is from Switzerland and back in Switzerland, in Lausanne. So the result is this one. So let X and X prime be a normal affine surface with S toric. If the automorphism group of X is isomorphic to the automorphism group of X prime, then X is isomorphic to X prime. So the automorphism group, sorry, wait. Oh, yeah, I don't know if I read it correctly. So you have two surfaces, X and X prime, and you only know this. This is the problem. This is an X. So I changed the notation yesterday and I forgot to change this one. This is here. So you take X and X prime, normal affine surfaces, and the first one, X, happens to be toric. If you have the automorphism group X and X prime be the same, then X and X prime were the same to begin with. So the code written in my blue bubbles here. So affine toric surfaces are indeed uniquely determined among normal affine surfaces, but the regular automorphism group. Again, nothing prevents that a non-affine surface or any affine variety of higher dimension could still have the same automorphism group of X. And also nothing prevents a non-normal variety to having the same automorphism group as X. So it's more precise, so we need more hypotheses to actually get the affirmative answer. So this is not yet published, it's accepted for a really long time in PISA, but it's not yet published. And we have two propositions that we can extract from there. So the first one is in the same paper. So we were actually puzzled by the fact that this normality here is required. So we were able to prove that actually in the same theorem as before, if X is the affine space, no, sorry. If we take one of them to be the affine space, not just any toric variety, but the affine space, then we don't need the normality hypothesis. So just any surface that is affine with automorphism group isomorphic to the automorphism group of C2, in this case, X could be non-normal, then it's not normal, actually it's the affine space. So this means that for the affine space, we could remove the normality condition in the previous theorem, but also Regeta had given before we did our stuff, an example of two toric surfaces, one of them normal, but the other one a non-normal toric surface, having the same automorphism group. So it was kind of open to explore whether and up to which cases, up to what cases you have a non-normal version of the variety and you don't have. And this was done by Roberto Diaz with myself, student of mine that happens to be around here. So this is also accepted, but very recently in IMRN. So let X be a toric surface. So there exists a non-normal toric surface, X prime, such that the automorphism group of X and the automorphism group of X prime are isomorphic. So if and only if X is not, okay, we had the C2 case and the two degenerate case. So the torus itself or the product of C with C star. These are called degenerate toric surfaces because they have torus factor. So actually the proposition we did, I mean, it's very easy to check the two degenerate cases. So C2 is actually the only one where really you can remove normality hypothesis with a proof, with an actual serious proof. For any other toric variety, you will have toric surface, you will have non-normal versions. And let me say a couple of things here. So the first, I forgot to say here. So this, the talk you saw by Andrew, most likely, I didn't actually check the, so here with Immanuel Stampfli, they recently they very recently proved the same theorem, but not for surfaces, but for varieties of dimension n. So actually, this theorem is kind of superseded by the work of Regeta with Emmanuel van Santen. So he changed his last name when he married. So Emmanuel van Santen. So they generalized the surface case to the general case. And I have to say the other two here. I put it in the next slide. So let me give an idea of the proof of this proposition first. So the non-normal one, because as I said, I guess you saw an idea of the proof of the first theorem, but I will give you some idea anyway. But let me concentrate more on this one. Here is the proposition. It's the same. I just copied. So I want to give you the idea, and what I wanted to say before, in all we did with Regeta, Urech, and here with Roberto Diaz, we use Joseph Seidenberg, both of them here, description of out X. Remember that X is toric surface. So they gave in a proof in a paper a very concrete description of the automorphism group of a toric surface, and we use it. So our proofs are not scalable to higher dimension because they need this part. I haven't read in full detail the Regeta van Santen paper, so they managed to actually avoid using this characterization of the automorphism group of toric surfaces. So that's very crucial why what I'm telling you only works for surfaces. We also use some results by Kanta that also work for surfaces. So it's very specific what we did. Okay, so the idea of our proof is very direct. So the first one is if you take C2, let's take the exceptional cases first. So if X is C2, is what we had proven before with Regeta and Urech, so there's nothing to do. Okay, if the variety is C star to the power 2, so the torus itself, okay, the torus itself has no non-normal models. So it's very easy to see that if you have a group, so a non-normal model of a toric variety is given by a semigroup whose saturation is the semigroup of the toric variety itself. If the semigroup of a toric variety happens to be a group, you cannot remove anything without breaking the product rule. So there are no non-normal models for the torus itself. And finally, for this one, C times C star, you can actually compute. In this case, it's quite simple because C star, it's a very simple variety. We know the automorphism group of C star. Yes, it's just translation times semi-direct with Z2. And then when you do cross C, it's like you have the affine, you see it as the affine line above this other variety, and you can compute the automorphism group. Quite simple. The same for product with a non-normal curve. So just computation. And in any other case, so in what we actually prove is that you take any other variety which is not C2, is not the torus, and it's not C times C star, okay, take it as the spec of a semigroup, so S is just a semigroup, and then if you take the set of irreducible elements in the semigroup, this is also sometimes called a Hilbert basis. So irreducible elements are elements that if you can express them as the product of two elements, then one of the elements has to be the identity. So an irreducible element is what you expect, no? Those that you cannot write as the product of two elements that are not the identity. Then what we actually prove is that the automorphism group of S, of course, if you remove the irreducible elements from a semigroup, you still have a semigroup because they were irreducible. So there are no two elements that multiply themselves into the element. It's a definition of being irreducible. So you can always remove from a semigroup the irreducible elements and you still get a semigroup. So what we proved is that if you remove the irreducible elements from the semigroup, you still get the same automorphism group. And as I said before, we do use this description of the automorphism group of toric surfaces, because we don't really prove that the automorphism groups are equal. We just prove that they both have the same torus and the same set of roots. And that's enough to prove the isomorphism using the result by Arjasov and Seidenberg. And so, as I said, what we actually prove is that the set of roots of x and of x prime is the same. So let me tell you what root subgroups are. Again, you probably all of you know, but I tell it quite quickly. So if you take a maximal torus inside the automorphism group of x is just any varieties here. So an algebraic subgroup U, which is isomorphic to the additive group, is called a root subgroup with respect to T, if the normalizer of this U contains T. So this is equivalent of saying that T and U actually span a group that is isomorphic to a semi-direct product of the affine of the additive group with the torus, and using the character, some character chi. So a root group is also uniquely determined by a derivation on the sheaf of regular functions of the variety, and you have to put some integrability condition. In the affine case, this is the condition is to be locally nilpotent. I'm not going to give the details. I'm pretty sure you all know what the locally nilpotent derivation is. And actually, the description of that Demasieux gave of the automorphism group is based on this. He defined this. Actually, even Demasieux, when he stated, he gave a description of root subgroups on toric varieties, even for non-complete varieties. They don't even have to be affine. He gave it for any toric variety. So this is, in that sense, most of the basic notions of everything were already done by Demasieux himself long ago. But in this case, we need to compute root subgroups of toric varieties that are not normal. And this is something that Demasieux did not took care of, because for him everything was smooth, and actually normality makes everything much easier. So this was really something he didn't do. And let me just give you what the description of root subgroup of non-necessarily normal toric variety is. Actually, we did it more generally. We just took cancellative monoids. So a cancellative monoid is not necessarily the monoid of a toric variety, even if you accept non-normality, because you could have torsion inside a cancellative monoid. So this is more general. We did it for all cancellative monoid, not just for affine monoid. Monoids that can be embedded into z to the power n, they are called affine. And also we only put finely degenerated when it's absolutely necessary. I just put it here to be safe, but it may not be even necessary for this statement. Okay, so take a semigroup, which is, take a cancellative monoid, not just any semigroups, especially cancellative monoid, and let M be a minimal group where S can be embedded. Actually, being cancellative is equivalent to the existence of a group where the semigroup, where the monoid can be embedded. So not all monoids can be embedded in a group. Cancellative monoids are exactly those that can. So we also take the dual group of M here, and now M could have torsion, but the dual group will not have it. So N is an honest lattice this time. And we can also take the dual monoid by the same definition you would take for the dual monoid in the affine case. And as I said before, S star and N now are honest. So S star is a monoid inside N, and N is a lattice, so it's a set to the power N. So this is an honest, like in toric case. So you can define rays, you can define anything. So this row, this here, I didn't wrote the definition, but S star to the power 1 is the set of rays of that semigroup. So a ray of a semigroup is just a one-dimensional face, and faces of semigroups are exactly elements that are sets such that if I add two elements and I fall into that set, to the two elements were in the set to begin with, for the usual definition of phase. Okay, so now let me read the actual definition. So we call a Demasure root. So a Demasure root is the object that is going to classify root subgroups and corresponds exactly to the weight that you used in this weight, this character you appear here. I don't use chi in the notation, I use alpha, but it corresponds exactly to that one. So an element is called a Demasure root if you know Demasure roots in the toric case, in the usual normal toric case, it looks very similar. So there exists a ray such that taking this ray applied to alpha is -1, and moreover we need to ask for m plus alpha to be in S whenever m is in S and we have that row of m is greater than 0. So if you have used Demasure roots in the normal case before, this is some combinatorial condition directly. It doesn't need to be tested in the whole semigroup, which is the magic of normality that allows us to see things with cones. But this is the definition you have to do. If you think for 1 minute, you will convince yourself that this has to be the right definition, and it actually is. It's not so easy to prove it though. If you want to do it in this generality, because the fact of having cancellative monoids, the allowing torsion into the monoid S, actually makes proof much more complicated, and you need to take some technical details into account. But you can prove the same result as before for local nilpotent derivations on the semigroup algebra of a cancellative monoid, which is stated here. This actually I copied from my very first paper ever. The same phrasing. So let partial B okay, yeah. Let delta be a homogeneous local nilpotent derivation of degree alpha, which is also non-trivial. In order to have a degree, it has to be non-trivial. Then alpha has to be a Demasure root of S, so satisfying what it's written on top. And the derivation I had actually can be obtained from this derivation. I forgot to copy, sorry. I forgot to copy the definition of D sub alpha, but it's exactly what you expect. Sorry, this is M. There. So this is the definition of this sub alpha, which I forgot to copy. So this is a description of Demasure roots, or of one parameters of root subgroups on, in particular, not necessarily normal toric varieties, or more generally on the spectrum of finitely generated cancellative monoid, which looks a lot like the previous case. And as I said, using this description, we can just go and compute in our original, our motivation was actually to obtain an example that has the same automorphism group. So you can actually go and compute the set of roots for this semigroup here, for this one. And you happen to find that they have the same set of root subgroups. Good. So I think I have 8 minutes left, so I'm not sure if, okay, let me just give you a very quick idea of the proof of the main theorem with Regueta and Uref, of the original one here.
I'm very sorry.
As I said,
I'm very sorry, but it's completely okay, okay to speak 1 hour and a half. So please don't hurry.
Ah, okay. I thought it was I thought it was an hour, so I won't hurry. But it will be 1 hour and 10 minutes, no more than that. Thanks. So let me also give you an idea of the proof of the original, as I said, the original first theorem with Regeta and Urech. So it's how we managed to prove that if you have X, a normal affine surface, with one of them, X and X prime, two normal affine surfaces, with one of them being toric, then if the automorphism group of X and X prime are isomorphic, then X had to be isomorphic with X prime to begin with. Okay. So we need to grab the problem by somewhere, no? And they actually grab the problem by something. The first thing we can do, we can actually, I said there is no algebraic structure in X, but there is a little bit of algebraic structure. So we can actually give a topology to Beer X. This is the way you can give the Beer X for any variety X. So let A be a variety and F be an A birational map, meaning that it's constant on the first factor, and induce isomorphism between open subset of U and B of X, such that the projections from U and B to A are both surjective. So this means this is a birational isomorphism from A times X to A times X, but that when I project into A, it needs to be surjective. So the open set where it's defined is not just any open set, but an open set that is surjective over A. So such map A, we're going to be calling them morphism. And by calling such maps morphisms, actually this is also everything. I've been rubbing Demasiur my whole life. So this was also done by Demasiur, but in a different paper. So this was, I think it's in the Anneaux Gradués Normaux by Demasiur, not the subgroup de rang maximum, the group de Cremona. So I should have said that at the beginning. This is also an idea of Demasiur. So the Zariski topology on Beer X is going to be just the finest topology, making all such morphism continuous. So the usual notion. And now you have to prove it, but it works. We've created ourselves a topology, at least on Beer X. Once we have a topology, we can start giving some structure into it. So we have here the first definition. So an algebraic subgroup of Beer X is the image of a morphism, like that being meaning continuous in the Zariski topology, that it's also a group homomorphism. So we have the idea of what does it mean to be an algebraic subgroup of the group of birational automorphism of a variety. And an element, of course, is called algebraic if it's contained in an algebraic subgroup. So being contained in an algebraic subgroup is what we just explained. So you have a continuous morphism from G into Beer X that it's also a group homomorphism. Okay, so with this definition, we can go to the key result, which is the way we capture algebraic information from the abstract group. So let G be a group. We're going to define a notion that is called divisibility. So in a group G, this is a group thing, nothing to do with algebraic geometry. So an element in a group is called divisible by n if I can take an n root. So if there exists an element such that G to the power n is exactly F. So it's a little bit annoying because it's called divisible because it's thought for additive notation. But since we use automorphism, we need multiplicative notation. So divisibility actually means taking roots. So an element is divisible by n if there exists G such that G to the power n was my element F. And an element is called divisible if it's divisible by all possible n from 1 above. So the key lemma that we use is the following. When you have now it's surface specific again, and because it uses results by Kanta that are surface specific. If you take a surface and F is an element in Vir X, then the following two conditions are equivalent. So maybe not F being divisible, but a multiple of F is divisible. That's one condition. And this is equivalent to F being algebraic. So you can see here we have the first one is a purely group theoretic notion and allows us to characterize the idea of being algebraic, which is non-group theoretic. It's being contained in a group action inside on X, in an algebraic group action. So this key lemma that is proven, as I said, using techniques by Kanta, is the one that allows us to tame the group, to hold control of it, because we can now know if an element is algebraic purely looking into the group structure, and that's the key point. So okay, but this is for Vir, yeah. You see, all this is for birational. We need it for regular, because our statement is for regular automorphism group. So here it comes. We need the definition of being algebraic for regular. So an algebraic subgroup of out X is the image of a regular action. Sorry, no. An algebraic subgroup of out X is what you expect, just the image of an algebraic action. And an element is called algebraic if it's contained in an algebraic subgroup, which means if it's contained in the image of an algebraic action on X.
And
so,
can we get the question?
Sorry? Yes.
Question, in this lemma, do we need really a surface? Then it was, in Kanta case also a surface. For higher dimension,
yes, in Kanta, no, for higher dimension, it's not no, it's specific surface. This one, up to my knowledge, it's specific surface.
Thank you.
Yeah, so, but as I said, I haven't read really Regueta and Van Santen papers, so I have to actually go check how they did it.
It's really a surface here. It's really a surface.
Yeah, here it's surface. It doesn't work if it's not surface. Good. Okay, so with this definition that I gave, which is the notion of being algebraic, but this time in the regular context, we can use the previous lemma to prove this lemma. So if X is a normal affine surface and G is an automorphism of out X, then X is algebraic in the X if and only if X is algebraic in out X. So being algebraic as birational element, as birational isomorphism, is the same as being algebraic as regular one. So now we can use both lemmas together to actually here the key point. So if you have X and X prime, two normal affine surfaces, and you have just a group homomorphism, abstract group homomorphism, any group homomorphism going from out X to out X prime, and if you take an algebraic element of X, then its image has to be algebraic. So if you have something contained in the image of a regular action, its image has to be also contained in the image of a regular action. So it's the first step into gaining some control. So the isomorphism between out X and out X prime that a priori was purely abstract, had nothing to do with geometry. It has something to do with geometry. At least it has to send algebraic elements into algebraic elements. And of course, the proof of this is just applying the two previous lemma, no? So the element is algebraic in the regular context, by the previous lemma is algebraic in Vir. By the lemma before that one, then it's divisible. Then divisibility is a notion that is preserved by group homomorphism. So you go to the other side, on the other side, the image is divisible, and then you come back with the lemma. It's divisible, it's algebraic in the birational context, and by the previous lemma, it's then algebraic in the regular context. So this proposition is just putting together both previous lemmas. And as I said, it's the key to actually being able to contain the groups. And now the rest is just, I mean, hard work. Just now you know that algebraic elements go to algebraic elements. So an element, and now what you do is just the same context as before. X and X prime are normal affine surfaces. One of them is toric, and you have a group isomorphism from X to X prime. Okay, you have a torus acting on X because X is toric. Okay, it has an image. You know that all the image of all its elements are algebraic. So they are contained in an algebraic group. And now you go see what do they span all together. Oh, and they happen to span a two-dimensional torus. So now you manage to to create yourself a two-dimensional torus acting on X prime. So now you gave X prime the structure of toric variety. Now you know that both are toric. We don't know that they are the same yet, but at least we're very far along. We know that they are both toric. And then as often, the only tool we have with affine stuff is root subgroups. So it's going to be root subgroups that create the final part. So if you take X and X prime, normal affine surfaces with X toric, again, X goes to X out X goes to X out X prime by phi. It's a group isomorphism. And you take a root subgroup with respect to T. With respect to the torus T. Then the image of this, it's also a root subgroup with respect to the image of the torus. So again, root subgroups go to root subgroups. So now you have mostly everything. You know that X sends torus to torus and root subgroups to root subgroups. But that's not enough, because I mean the set of root subgroups and the set of root subgroups of almost all toric surfaces is the same. It's just two infinite sets. But to finish the proof, again, so it's here. So we know now that X prime is toric surface, and we have a bijection of the root subgroups of X and X prime with respect to the corresponding torus, which is T, and the image of T. So to conclude the proof, the only thing we need to do is that we actually it's not clearly stated here, but the root subgroup goes to a root subgroup with the same weight, and it's preserving weights. It's not written here, preserving the weight, the character alpha or key. Preserving weights, that's the important part in this lemma, which is not written. So now we know that X and X prime are both toric, and they have the same set of roots. We have a bijection of them, and we know that they have the same set of weights. So to conclude, the only thing we need to know is actually show that we can recover a toric surface from the abstract group structure of the root subgroups and the relationship with the torus. So just by knowing the weights of the root subgroups. And this is purely cooking techniques. I didn't wrote it because it's awful, but it's just purely cooking techniques. You can see in the paper, we just take the intersection of two kernels, something very strange, and then this gives you the D and E. So you know that any toric variety, like this one, is going to, I don't know, they are often called D and E, with D and E being integers relatively prime, and no, I don't remember exactly. But an affine toric surface is characterized by two integers D and E with some duplicity. So if there's another E prime that characterizes, but what the only thing you need to do is go and pick this D and this E to see if you can recover it, and you can't recover it by some very awful cooking techniques. So just taking some intersections, some very strange kernels of root subgroups, and what you obtain in the end is a set whose it's a set that have, how's it called? So it's an arithmetic progression with distance d, and then you create yourself another arithmetic progression whose distance is e, and that's how you recover d and e. So it's purely cooking techniques that I'm not showing. So with this, I really conclude the talk. Thank you very much.
Alvaro, so thank you
Yes.
very much. Dear colleagues, any questions, comments?
So this recovering of the toric variety from the Demazur roots, whether this can be extended to higher dimensions?
Yes, that can be extended. Well, actually, we did it. So I removed it from the talk because we then proved. So we wonder about higher dimension, and there we didn't have how to handle that. The main point we're missing is torus goes to torus. So once you prove that, you can do everything else. And actually, this cooking technique, it works in general. It doesn't require surface case. So the structure of the relative position of the roots with respect to each other determine the toric variety.
Okay.
And actually, so
any toric variety.
Any toric surface. And sorry, any affine toric variety.
Yeah.
So so we were able. Let me see again. So actually, we can actually prove this not surface but variety. But this has to be an isomorphism of in-groups. So that it sends torus to torus. But since this was recently actually removed by Regueta and Van Santen, I actually just cut it from the talk. I removed the 3 slides because I don't think it's interesting anymore. I mean, there's a stronger version, and you had the talk, if I understand correctly. Andrew gave a talk on that here, but we can prove that with the in-group in that paper.
And another question, you developed the notion of Demazur roots in your paper with Kevin Langlois in the positive characteristic case.
Yes.
Whether this theorem or
I hate positive characteristic, and I hate it even more now because we also did with the same Roberto Diaz that is sitting around there, and with Adrian Dubulo. We did not this particular setting, but we did for in-groups, for GA action on in-groups. So you need to get some pro LND, stuff like that. And we did the characteristic P, and I think it's awful. I'm pretty sure this works. I'm not going to do it. But yes, I'm pretty sure you can state the exact same theorem. So with Kevin, we proved the equivalent of this theorem, and the statement is the same. I'm pretty sure the statement is going to be the same for positive characteristic, but it's proofs they are really awful because you have to work with this higher order iterative derivations and stuff. So I have no doubt it's true, but unless it's mandatory, I don't do positive characteristic anymore.
Okay.
So if someone wants to do it, I'm very happy to be the referee for that paper.
Okay, dear colleagues, please, more questions, comments? If none, then I have some list of questions even.
Okay.
I wrote it down during your talk. May you return to this theorem by Filipkiewicz about most manifolds? So it looks like a great fact. So this is, I don't know, how the nature look like. Is it deep result, something from Annals of Mathematics, or this is not?
Yes, I think it's Annals of Mathematics itself. It's really deep result. And actually, it has many generalizations. It's for people from differential geometry, he's kind of God.
No, it was not in Annals.
I don't know, but it's a very important journal. I don't remember, but I have the paper. I can look for it.
And don't you know how difficult is the proof? So what is the idea?
No, no idea of differential geometry. I just pick up. Actually, this was someone told me when I gave this talk that this was this result guy. I looked for the paper, and actually, this is a deep simplification. He does it for CK diffeomorphisms and not for just what we understand by differentiable manifold, but he doesn't need them to be even compact. I think paracompact and some others for some very. Yeah, someone knows better than me.
If I may say, if I remember correctly, the main idea is it goes back to Whittaker, to his paper from 60s. And the idea was that you take a stabilizer inside of the group of diffeomorphism group, which stabilize one point. And you basically show that the image of the stabilizer of one point is again the stabilizer of some point in the target. And in this way, you basically construct the map which sends one point to another point, like point. So you make a correspondence between point and stabilizer in the group of this point. And through this trick, you construct a map from one variety to another, and essentially shows that this map is a diffeomorphism.
I didn't realize you were here, Andre. So yeah, you should answer. Actually, maybe you can better answer what I answered to Mihail. So is this correct? No. So what you prove with, wait, am I correct that what you prove with Emmanuel is, where is it? Is exactly this without the in-group, no?
Yes, it's this without an in-group, yes.
Perfect.
Okay, then the next question from my list. May you return to the slide where you mentioned de Mazur for the first time?
I don't know where it is. Is it probably this one?
Yes, yes. And when you spoke about this, you said something like de Mazur's proofs and results are valid for any toric variety. I understand that his description of the automorphism group, they are valid not necessarily for smooth, but for arbitrary complete varieties.
Yes, but exactly.
Completeness assumption is necessary, and you said
complete is necessary for the full automorphism group, but that I said when I said about roots. So the result about roots is true for all toric variety, and the result about automorphism group is exclusive for complete.
So we know description of all root subgroups for arbitrary toric variety, but we don't know whether they, together with torus, whether they generate the.
No, we don't know if they generate, because if we knew that, we will know the automorphism group of Hn, no?
Okay, so this is just. Okay, and then one more question. Can you go to this slide with the divisible elements in birational automorphism? I would like to ask about this first condition in the lemma. So not necessarily f, but some of its power should be divisible, right?
Yes, because you could have a finite group, for instance.
So I would like to understand what does it mean. Divisible means that it is divisible by all integers.
Yes.
Positive.
Yes.
And you are allowed to take some concrete power. Does it mean that your original element f is divisible, but almost all positive integer except for finitely many? And this passage to the power allows you to add divisibility by this finitely many exceptional elements.
No, I don't think so. No. So if you take the group, just Z over 2Z.
Okay.
So Z over 2Z, I think, so the element 1 is divisible by even numbers, no? By odd numbers, but not finitely many.
Yes, the problem is with finite elements.
The finite elements. So you see, in the group with 2 elements, the non-trivial element is only divisible by the odd numbers.
Ah, I see. By this passage to the power, you somehow
passage to the power allows you to take the finite part to 0, to the identity, and the identity is divisible by wherever you want.
I see. So when you work with the automorphism group as an abstract group, you should use something like order of elements, this divisibility.
Exactly.
and then you try to implement it for torus goes to torus.
Exactly.
Because originally the concept of torus doesn't make sense because you consider abstract groups, right?
Exactly.
Okay. Maybe as a last question from my list. Concerning this description of automorphism group of non-normal affine toric varieties. I know that it was a publication by Sergei Gayfulin, who is here, and Ilya Boldarev, and they also describe this automorphism group. So
I know, we read it actually. They describe, they give a very strange description because I wish is he here, because they describe, yeah, they describe, but not all of them. I think they only describe what they need in the paper, in their proof. So actually, we even put a remark in our paper that we actually think that with our theorem, it's possible to simplify some parts in that paper. Because I don't think they gave a full description.
Sergey, didn't you have a description of all of the subgroups?
We have not the full description of
exactly.
Yes.
I think you did not, but you had it. I mean, you just didn't wrote it. You can take it from what it's in the paper. We stated in our, so we have after the theorem there is something like a remark or something saying exactly that.
Yes.
So in their paper, but I think they just concentrated improving what they needed for the main result, not the full description. But yes, they intersect for sure.
Sergey, maybe you can comment what have you done in this work?
In our work or
in your work, right?
Intersections. I think the only intersection is maybe the concept of de Mazur root. So it seems that intersection not very big because just for toric varieties is very simple. You have a de Mazur root of normal toric variety, and to be a de Mazur root for non-normal, you should move all the semigroup and have points in the semigroup, and this is the same. But it seems that this is the only intersection, something like that.
Yeah, and actually, as we speak, I'm trying to look for the remark we wrote in the paper. I'm very good at forgetting what I write. So we wrote it, and then I completely forgot. But we did wrote some remark, like kind of describing what we understood was the intersection. But I mean, with the full description, you could simplify some stuff. That's what I remember the most. So if you don't have any more questions, can I ask a question?
No, stop. Okay, so let me again ask the audience: do they have any more questions?
I have one.
I have one.
Okay, so please, questions from the audience, and then
okay.
Thanks. You said that toric varieties can be recognized by its automorphism group among all the varieties normal. Do you have examples of non-toric varieties with such property? Do you have examples of non-toric variety which have unique automorphism group which is not isomorphic to any?
Yes. So Andre, can you answer, please?
I mean, did I understand correctly that?
So other instances of the theorem other than toric, you should say.
Well, we have something about the Danilevsky surfaces, right?
Yes, but you had some more precise result with Matthias, no? Matthias Leuenberger.
Yes. So I mean, basically, what we have with Matthias is the following. So, or it's a consequence from Matthias. So basically, we have that if you have a Danilevsky surface, smooth Danilevsky surface, and any other surface, not necessarily normal, any surface, and if the automorphism groups of these two varieties are isomorphic as int groups, then varieties are isomorphic. But if they are isomorphic only as abstract groups, then there are counterexamples. Then Levski surface is not determined by its automorphism group.
Ah, sorry. So actually, there's no other category where you can say yes without the int group condition.
Well, maybe spherical.
Spherical varieties
Maybe
are
spherical.
not toric.
Ah, spherical. Yes, spherical. Yes.
But smooth spherical.
Yeah, smooth spherical.
And it's not published yet, just for non-int group case, but proved. It's not published, but proved. But again, smooth. But again, up to some condition, because with spherical it's much more difficult. So we know that toric variety is defined over Q, over rational numbers. And we don't know this for spherical varieties. So what we know for spherical varieties, we know that spherical variety is defined over some finite extension of Q. And this makes a lot of problems for spherical varieties compared to toric.
Okay, so dear colleagues, any more questions, comments? If not, then we have an exceptionally strange situation, a question from our speaker. So Alvaro, please.
Yeah, it fits very well into the subject. No, it's just, Andrew, can you just give us in 3 minutes the idea of how you remove this int here? How do you get the torus to go to the torus in higher dimension? So that I don't have to read the paper, or I read it knowing what to expect.
I mean, so there is this result with Sesh and Juni.
Yeah.
And basically it says the following. So if you have a connected commutative subgroup in the automorphism group, then it's nested. Then it's a union of algebraic subgroups. And that's exactly what is used, because you see now, if you take a torus in out X, you know the torus coincides with its centralizer.
Yeah.
So you take the image of the torus. Now you know that the image of the torus is closed subgroup because it coincides with its centralizer.
Yeah.
You don't know if it's connected, so you take connected component. And now this connected component is commutative. So you know that connected component is a union of algebraic subgroups. Now your task is to show that this this union of algebraic subgroups does not contain a copy of GA.
Okay.
How you do it is tricky. So it's like 3 pages work essentially to remove the GAs. So I mean, very roughly, you take root subgroups in out X. So your torus acts on these root subgroups.
Okay, but then the part of seeing that it's not additive group is just hard work. It's not like you're not using like some big machineries. Go hard work and check everything.
No. It's it depends. We don't use machinery. We use tricks and structure of the automorphism group effects.
Exactly. Thank you. I'm happy with the answer.
Okay. If there are no questions, including questions from the speaker, then let us thank Alvaro for his beautiful talk. In my opinion, very nice and deep results, and also very nice general presentation, motivated and good motivation from other branches of mathematics to study this question. And I think that we may expect further results in this characterization by automorphism. Not only for toric varieties or for the Levski surfaces, but also for other types of varieties. So let us think about this.
So thank you very much.
Okay, so let me announce and recall to the member of our lab. In January, we will have a talk by Professor Baohua Fu from Beijing. It will be another subject. It will be about mirror symmetries for nilpotent orbits. And it's also very interesting to our lab, and we invite all our guests to participate in this talk as well. Okay, so
See you.
thank you very much.
Bye.